I'm excited to talk about ultra-high performance gradients, specifically the connectome and the impulse. And from the fMRI perspective, those are quite different, very high performance machines. They're high performance, no less, but they're quite different. And today I would like to show you how maybe fMRI folks see them differently than the diffusion folks. For us, as well as for diffusion folks, we care about this trapezoid, this big, almost scary trapezoid. And we care about this not only for contrast encoding, but mostly for spatial encoding, traversing K-space. And while those two different geometric shapes here are very, very simple, my 6-year-old son understands those, there's quite a bit of knowledge you need to have to understand them very well. And there are these hundreds of different parameters that you need to control them. And so for the sake of this presentation, I would like to dumb it down to, or like to simplify it and oversimplify it to 2 parameters, namely the slew rate and the Gmax, that ultimately give me my resolution and my echo spacing. So for any given resolution that I want to have at a given scanner, I can be either slew rate limited or Gmax limited. For example, when I want to have a given resolution and my scanner ends up giving me this kind of triangular shape, I probably chose a too low resolution for that scanner, and I'm slew rate limited. And I define this as being the fact that when you increase your Gmax by 10%, it doesn't really buy you that much. But if you increase your slew rate by 10%, it buys you a lot. Now, you can also be on a different case where you are ending up with these more rectangular shapes, which probably means you chose a too high resolution for your scanner. You're Gmax limited, defined as the fact that if you increase your slew rate by 10%, it doesn't buy you that much. But if you increase your Gmax by 10%, it buys you a lot. So ideally, you want to use a scanner that has this balance of slew rate and Gmax for fMRI, where you are neither slew rate nor Gmax limited, where the same 10% increase in slew would buy you the same as 10% in Gmax. And we have a lot of nice scanners available, and we have seen this kind of spectrum already. So we can see what is the perfect resolution within this space across the high-performance scanners of the SIMA-X and the Terra-X and the ultra-high-performance scanners of the Connectome and the Impulse. And maybe the first thing that is very different for us fMRI folks compared to most of you diffusion folks is that our y-axis is kind of constrained. We are usually not allowed to use even like 30% of the Gmax here. We are down there, which is mostly due to heating. It's not yet a 12-time problem, but it's mostly heating of the gradients or the GPAs for that matter. So for example, on the Terra-X, when I want to use only 40 millitesla per meter, after 5 minutes of scanning, usually my phone starts to vibrate and I get these alerts, oh, your gradient is heating up, watch out. And if I continue to scan for another 4 minutes, then I'm getting into this dangerous regime of the 60 degrees Celsius where I might need to answer questions from the core. So I'm quite limited with respect to the Gmax, and I'm also on these high performance gradients. Usually then it's not the gradient itself that heats up, but it's more the GPA. So we have this smaller regime down here, which is still an exciting regime. And now I want to blow it up, going up to 200 slew rate. And I can see which scanner benefits me having this optimal shape where I'm neither slew rate or amplitude limited across these different scanners. So imposing here the optimal resolution. For example, for the Connectome scanner, it's really a mesoscale scanner. It has this kind of shape when you use a resolution in EPI of 0.36. If you use a lower resolution, which you're kind of leaving Gmax on the table. You're not really benefiting from the Gmax that you have. You're then slew rate limited. If you go to the SIMA-X, it's more in the range of 1 millimeter. For the Terra-X, it's really a macro scale scanner in this sense here, because the optimal resolution would be 2 millimeters. You can use it for high resolutions as well, but then you're leaving a lot of slew rate on the table and you're limited by Gmax. Similarly, for the Impulse, it is a very, very efficient macro scale scanner, but ultimately, if we use any resolution that's higher than 1.5 millimeters, we are less limited by slew rate, we are much more limited by Gmax. And superimposing here the echo spacing, you can see that it's very, very efficient. You can still use it for these mesoscale imaging, however, then you're leaving slew rate on the table, as I said. So having the spectrum of these different gradient shapes here opens a spectrum of low resolution, very fast imaging, or very high resolution, slow imaging. And I would like to show you some of those examples because after all, I'm in the application session, and maybe starting with this resolution, which I like a lot. And I like it also because this is just about the perfect resolution that you can have on a Connectome scanner. So when I visited New York for other reasons as well, I was sneaking in this additional 3D EPI protocol here, where you can see the exquisite details, even at 3 Tesla, to see these veins, these little stripes, how the veins are going into the cortex. And because the SNR is so nice at the surface, you can get these leptomeningeal renderings there. They can clearly see in fMRI where we would expect kind of signal displacements, how the oxygenation changes are traversing to the big sinuses. When you want to get those kind of resolutions on the fine-Bergertron, aka the impulse, you would end up with a different shape. Maybe I can hide this here, which is a bit more rectangular. So you're kind of leaving slew rate on the table. You're only benefiting a bit from the slew rate. You can still use it, but your Chi max limited. But nevertheless, we were quite happy when we got those kind of images that are already maybe 5 years old or so, because at that time it was unprecedented resolution. And for me personally, it really lifted the curtain to a new world of mesoscale imaging, to see all these interesting details down there. For example, we have these conventional fuzzy blobs of activity, but then also we have these very fine scale blobs, the diving veins coming in. We have layer features, and then also we see surprising things like these negative voxels that deserve more attention, and I want to talk about. So while we are not really benefiting from the slew rate so much, we might as well then also go to the Terra X scanner and making it a bit more rectangular even, where surprisingly we had a lot of artifacts, specifically because desired Chi max was not really as stable as I would wish. You can see this here on the scope measurements, where you do see that we have these ringing effects that across the different phase encoding steps, Chi max is slightly different, causing those artifacts. So when you disconnect your third order shims that cause these ringing, it's much more stable, and you can get artifact-free images to really appreciate the different spatial scales of fMRI activations here. Anything from the macro scale in the range of centimeters to the smaller vessels in the range of millimeters, these leptomeningeal vessels that have very interesting positive, negative activations. Then another order of magnitude smaller, these pile vessels in the range of a few hundred micrometers that also have very interesting dipole-dipole interactions, until you get to these diving veins in the cortex. And then only the 6th order of magnitude of spatial scales then finally gives you these stripes, these cortical layers that we care about, specifically for connectivity then later. And because this is EPI, you can do this isotropically. You can follow these vessels and their patterns across the orientations in 3D. And because it's EPI, anything that's dark is a vessel. So if you take these EPI data and invert the contrast, anything that's bright becomes a vessel. So you can pump this through segmentation algorithms and then basically follow these blobs individually along the individual vessels to see where they're connected to, which is relevant because all of these negative signals that we are getting here mostly are connected to large arteries. So we have some vasodilation effects here in gradient echo bold. So while we are not really taking advantage of all the slew rate of the impulse for those kind of acquisitions, there are other protocols that allow us to take more advantage of these high-performance, ultra-high-performance gradients. For example, when you lower the resolution a bit but want to be fast. And one of the applications that really benefits from those scanners then would be vaso layer-dependent fMRI at 0.8 millimeter for whole brain imaging. Because there the challenge is that in these inversion recovery sequences, we need to acquire 2 images along a single inversion recovery period after this inversion pulse that is played out every TR. And due to the physics of the blood T1, we only have about 2 seconds available to acquire this image, which is just not possible with a conventional Terra X scanner. So we want to have 2 images, whole brain, sub-millimeter, in like 4 to 5 seconds. And when you take these and apply them on the fine-Bergertron, the impulse, you do learn the lesson that with great power comes great error. Like as you are scaling your gradient strength, you also are scaling your gradient errors. And you have these fuzzy ripples, these shading patterns over here that can be taken care of by doing a dual polarity EPI approach that then cleans up those artifacts, and you can get a beautiful whole brain pairs of images within single inversion recovery periods with blood nulling and without blood nulling. And this then allows you to do whole brain layer-dependent fMRI connectivity across the canonical networks, as well as these networks, also including the deeper brain structures with high spatial features and down there. When I say that with great power comes great error, I don't mean to say that these high-performance gradients are low-quality gradients, right? For example, as Iliana said, if you like dumb them down to use the gradient performance as you would on a conventional scanner, they are much higher performance gradients with higher quality. And I would like to make this point on this slide here. When you can play out a conventional like dummy trapezoid of 39 millitesla per meter, if you do this on a Terra X scanner and look at this after a ringing period, you get these ringing artifacts, right? When you disconnect your third order shim, these ringings are highly reduced. However, when you do this same dumbed down trapezoid here on an impulse scanner, this ringing is even further reduced, which is maybe even more relevant for the redirection EPI, the X direction, where you can characterize this with these GIRFs, gradient impulse response functions, where you do see that for the conventional frequencies, these high frequencies are kind of suppressed, first of all, but then you have all this chunk over here, these mechanical resonances. And this is usually the regime where we need to acquire our mesoscale images, having these kind of artifacts here. So when you disconnect your third order shim, these artifacts disappear and it's kind of smoothed out. And these mechanical resonances are really reduced by an order of magnitude. However, when you do the same thing on an impulse scanner, it's almost perfectly flat, right? So you still have these forbidden frequencies and these mechanical resonances that do become a problem, especially also the beat frequencies of multiple of those. But if you play out the same pulse on an impulse scanner as you would on a conventional Terra scanner, it's much higher quality. Moving from these rectangular shapes to more triangular shapes, fMRI can also benefit from these ultra high performance gradients by doing fast imaging. For example, as shown from Qinghuan's Candy Lab, Sarah Nolan made these animations of the signal fluctuations across the cardiac cycle. And the interesting thing is that there are a lot of very fast features across the cardiac cycle. For example, zooming in here, you can have multiple peaks along the cardiac cycle. Sometimes it's the first or the second peak that's stronger. And this inspired then also Stefano Moya from Maastricht to apply for one of the dissemination projects for Susie's scanner to look at the ratio of these different peaks, because these different peaks are indicative of blood pressure. So we are trying to use these pilot data then to get these blood pressure maps. And when you're not interested in fMRI, but diffusion, you're less sensitive to these specific shapes of the gradient pulses, if it's more rectangular or triangular. Because then you can get the same area under the curve. For example, when you compare the high-performance scanners for diffusion. And this is something that David Feinberg was interested in, to compare the impulse with the Connectome scanner, the two best scanners in the world, which reminds me a bit of comparing Mozart against Beethoven. And of course, these are kind of different scanners. So you need to choose your comparison domain wisely, because depending on which environment you're comparing them, one might win or the other. So David, I believe, was inspired by Susie's paper to choose this comparison domain, to use very high B-value with low spatial resolution and minimal Krappa. And when I was scanned on both of those scanners, they found out, and Joseph is here, that actually both of those scanners can achieve very good TSNR for these astronomically high B-values here. And then specifically in the center of the brain, where the high field has this particular advantage that the impulse can even outperform in this comparison domain here. And I'm not sure how much time I've left, but maybe there's one more point I want to make, namely that fMRI people, they are sometimes conservative, and they really like their data consistency. And they sometimes don't want to trade off consistency with high performance. So in my experience in the last few years, I found that cognitive neuroscientists, fMRI folks, they sometimes want like consistency over performance in a kind of Henry Ford assembly line production. They want to be absolutely stable. It needs to taste the same if it's tomato season or not, if it's like stable. Whereas, however, these ultra high performance scanners, they are kind of prototypes. You can get better quality, and we have very excellent chefs here that give you the best quality, but there's maybe a bit of variance in there, and you need to be patient with your scanner. And I learned this also from Bay 2, that when some fMRI users, you give them one protocol, it's 2D, it's with the third order shim, as the scanner develops it, it's stable, there's no risk of failure. Or you give them this other protocol, it's high performance, it's 3D PI. Yes, you need to reboot your scanner, you need to configure it, and it might fail sometimes. Guess which one they choose, right? So I think in the next few years, we need to have a kind of trust building campaign to make these ultra high performance scanners interesting for fMRI folks and show that they can be stable if we do it right. And if you want to hear more about fMRI at ultra high performance gradients, come back in November 5th. where we will have our launch impulse opening symposium, and do register soon because we are getting close to capacity already. Thanks for your attention.